here I have q plus cg to the 5. So I keep the linear time indeed. So I have 5 to 4 g, 5. Right? Okay, so I have minus d lambda q plus t d times this equation for p. So what I choose is that I choose that this is lambda q. Okay? I choose it like this. I mean, this is my choice for the lambda q. For q. Since there is a derivative, and since lambda q is not of integral 0, here I have some trouble, and this says that the t is not integer, right? But I told you it's not a specific form. So this is my choice for t, and if I do this, then this term will cancel out. Okay? So the V order cancels, so it's a better approximation, and makes a lot of difference. And then I also have, if I do a bit better, I have no time to do it, but if I do a bit better, here I forgot lambda square, I guess, or cube, I don't remember. But if we do a better analysis, we find lambda square dt plus 2t square is 0, which is my third equation. So I have three equations, and d is equal to lambda t lambda square. I have this equation, which is when I look at the second order d here, which is not, it's a very easy computation, just write the square, the d square. And then I have this equation. So I have three parameters, three equations, and they are very simple to solve. So the parameter x of t for the moment does not have any influence on the dynamics, just that we well, it's black for the position of the solution, but not on the rescaling of the parameter. So I don't need to rewrite the equation. I will just say that if I do this, wait a second. So the good quantity is the following: is this d over lambda square. If I time differentiate d over lambda square, I find d over lambda square plus minus 2 lambda t over lambda, etc. And I use the equation on these two equations, and this is equal to the 2 here. Very important, the constant, this we find 0. Okay? And this, in fact, is very easy to understand if you go back to the energy, because in fact it is related to the energy of QD. So the energy of QD is a simple computation. This is the energy of Q minus CQ. So CQ is a constant. Okay? Now, if I rescale, right? Oh, yes, of course. I'm sorry? What do you mean by not bounded? Well, in fact, the P is in H1. The derivative is fine. But it's not a problem. So I do have a square here. Otherwise, I have yes. Well, in fact, what we do is we cut off, and this time I put the square. But in fact, if we write the same thing for the epsilon, you're completely right. It's not even it's not a power 2, but it's a power which is bigger than 1. So it's very good. So when we put lambda here, and of course change is 0, then it's just 2 is 0. So here we divide by lambda square. So this law that we see here is just we will just remember the energy function, right? But I will tell you why I don't see this way, because this is a very particular feature. What happens is actually that this cannot be a solution, because you always have an error term in this computation, right? And also you don't only want to study solutions that have specific initial data, as QD, right? So in practice, you want to understand all solutions, so you have to decompose Q, D, of C, but you want to add some error term, like an epsilon, with K, right? And when we do this, we actually have three parameters that are needed to understand the dynamics, but we can slightly adjust the parameters so that epsilon satisfies three of the dynamic conditions. And this is very important to keep that direction in the way we control the epsilon later on. So if I just write, so I just say that with the solution, I put everything into the equation. So for Q, E, everything happens as here. Okay? And what is not zero, like the g to the cube or some term like that, appears in the equation of epsilon as an error term. So epsilon will satisfy a linearized equation, or a fully linearized equation. We still have non-linear time epsilon as well, but epsilon is going to be small. And then we have an error term for the equation of epsilon, which is due to the fact that QB is not exactly a solution. And we have to cut off, and so the cutoff has to induce some error term, etc. So but we have an equation for epsilon which is pretty nice. It looks like the AB equation with a potential which is Q4. And what we can do is we can do a kind of asymptotic analysis for this epsilon, which is similar to what we did for asymptotic stability of the solution in the subcritical case. And even if we are in a Bloch situation, or if we are in a J-focusing situation, like in the exit case, or in the solution situation, or in the Swiss situation, we are able to control the epsilon. Okay, so I will say a small result like this. So let me just finish the argument here. We have d over lambda square then which is a constant, right? And this is the same as lambda t, because v is lambda square lambda t. So lambda t is constant. So if L naught is negative, lambda is a positive parameter, so it will go to 0 in finite time. So this is the graph. And if you integrate back to the graph, we get lambda t is L naught t minus t. And since lambda is 1 over the h1 normal 0, we get the growth rate. It's written here. If we have lambda naught is 0, it means that the scale does not move. This is a solution situation, so just stay still. And if lambda naught is positive, the lambda increases, and this means decoupling. That is, the lambda is, the solution is flattening. But this flattening goes jointly with the fact that epsilon becomes bigger. In fact, the t becomes bigger as well. The epsilon becomes bigger, and we go away from the solid. And this is the exit. And once we exit, we have no more argument. But we have to stop the analysis because we don't know what to do after. So, and this is in contrast with the situation that we have dealt with Lacanissian flag or bigger Lacanissian flag that were able to do classification around soliton for the nominal and Gordon equation. For example, I call nominal weight equation. And they were also to control, they were able to control outside the soliton by proving no return lemma. So we do not have such no return lemma for the KGD equation so far. So once the solution exists, the neighborhood, we don't know what happened really. Okay? We just know that it's very flat, it's close to the mean solution, but we don't know more. Okay, so from this we see the three cases. Now if I take the full solution, we have the epsilon part, that we need control. And this is controlled using a Lyapunov functional that I cannot write here, but I will call it f of t. And the Lyapunov functional is, let's say, it will be controlled above and below by h1 norm of epsilon times a weight function. The weight is exponential for y negative. For negative y, so it's a localized norm. I'm not able to control the epsilon everywhere. And for positive y, it's like y squared. And this is why we need a weight on the initial data. And we need y to the 10, by here I put y to the 2, where we need some more. Okay? This is why we have to load at some point, so we put y to the 10. So it's kind of a strange quantity that looks like the energy at the level of epsilon, plus some Dirac density at the level of epsilon, so it's a mixed quantity that we control at the end, that will be decreasing, so we're going to prove that f prime, plus a positive quantity, let's say a local quantity, something like this, dy, which is negative, but in fact will be controlled by t to the 4. What we have t to the 4 is because in the equation we have t to the 2, d square. To form this energy vertical equation of epsilon by epsilon itself, and we go to Cauchy Schwarz. The epsilon part is absorbed in this term, and then we get, by Cauchy Schwarz, we get the d square, so we get the d4. So if we improve the answer, we improve this part. And to prove this, we do need that y has a good decay on the right, the good decay for y positive. But at least we get a nice way to control the epsilon. So I cannot say more right now, but we do have a nice control of the infinite dimensional part of the solution, besides a complete knowledge, I would say, of the finite dimensional analysis, which is just this kind of thing. So in reality, of course, when you mix everything, you have something like this. So 0 over lambda square is not really constant, of course. We get something like this. So the variation of 0 lambda square between 2 times is controlled by something like this, coming from the equation, plus, let's call this n of t. So it's a square of the norm of epsilon, or lambda square of t1, for example. And there's some other control for that. So what you see that 0 lambda square is not really constant, but it depends only on what happened at the time t1. Okay? And of something which is of higher order, because it is more. So 0 lambda square is not constant. Okay, see what happens. Okay, so I will lower my ambition, and I will try to give some ideas on the exotic graph. Okay? The point is to understand, in fact it can be done very quickly actually. So I will just draw a picture so that it's more clear indeed. So the point that I didn't mention so far is the x of t, you see the equation of x of t. Xt is 1 over lambda square, so it's 1 over t minus t. Okay, so if I integrate, x of t is like 1 over t minus t. You think that the graph point is going to infinity on the right. Okay, so if I do a picture of the situation, we have the following. So my initial data is q plus some perturbation, but it's nicely behaved here. I don't mind too much what happens here. I just have an h1. This is initial data. So if I am in the graph situation, this will start computing, and we move to the right very quickly. Right? And when I'm close to t star, when I'm close to t star, the structure is very focused. Okay? Its location is at most 1 of t star minus t. Right? So it's going very fast on the right. And here it's a plus and factor. I have the decay, and the decay is going to miscale, so it's very small. And the residue of the mass is going somewhere here. In fact, for the KGD equation, big objects travel very fast. Right? Whereas the small object cannot travel so fast. They don't have enough h1. So I have a decoupling which is which is very important in the proof. And that is why we can show actually that epsilon goes to 0 very fast. In fact, from all this we can prove that this norm in fact goes to 0 like in the Risch time, that's 1 over t to the 7, for example, something like this. So it goes to 0 very fast. Whereas the remaining part of epsilon does not go to 0 in L2, it's just a residue here. And then we work in finite time. But the finite time will have a residue, so we can call it U star. Okay? And this stays in compact set or something. And this is going fast to the right. Okay? So this is, I would say, the standard graph, the graph in A. So now, what is the strategy to get exotic graph? So for the exotic graph, what I will do is that I will do the same strategy, but on the background, on the bad tail. So I put the tail, an explicit one, the power of x, which is L2, which is NH1, sorry. I will put the solution on the top of it, and I will expect that the interaction between the solution and the tail will change the dynamics. In fact, I will complexify a little bit the equation, which is very simple. It's lambda t is constant, right? So far I have lambda t is 0. Okay, so that's very simple equation, right? So what we expect that if we put the tail, we will change this equation for another one. Whereas the tail will have a strong influence. So this is what will happen. So the tail I'm talking about is the following. So I define x naught of x is a constant, which happens to be negative in our example. X to the minus theta is to be chosen, but it will be chosen around 3 over 2. Technically, so a bit bigger or a bit smaller. So this function is indeed in H1 and N2, and this is only for x, right? And you do whatever you like for on the left. Okay. What you said that this is a monster solution of the KdV equation. Because if you differentiate with respect to time, it's 0. It does not differ on time. This is not moving, right? It's a fixed state. So I put it here once more. So I put the tail like this. So it's negative, but and then I will put my solution on the top of it, right? This is a monster solution because when I differentiate with respect to time, it's 0, as I said. When I differentiate with respect to x 3 times, of course it's much smaller because x is large. But take power 5, also it's much smaller. So all this is negligible, right? So I can do as this as not one solution. So I do the following. I consider a solution which is u of tx. I do the same way as before. I say it should be epsilon with k, and I add this. Right? This is a solution, right? This I expect to be a solution, but so the equation of epsilon, which is the same as before, except that in the nonlinear power, in the nonlinearity, I will have interaction between S naught and this guy. And of course the figure 1, this is more because I have large x. So the figure 1 will be the 2 to the 4 times this power 1 here. This is the biggest interaction I can imagine. Okay? This is the only interaction I have to take into account. So what we do, we write the equation for epsilon, and we do as before, and we add a term in the equation. But the simplest way to see it is to do the energy conservation. So what happens for the energy of this? So I told you before that the energy of QB, lambda, was g over lambda squared. That's the constant, right? So I do the same, but now I have to consider that I have not have the energy of Q, of QB itself, but QB plus S naught. And in the energy, when I look at the gradient, it's a derivative, so it's a lower order. So what is the main term, as I said, is in the energy to Q to the 5 times S naught. So in the energy, what I get is so constant g over lambda square, and then I get what is going to be important is the Q lambda 5 S naught. And this guy is moving, this guy is not moving. Since it is focusing, right, so what I expect is this value here is almost 1 over xt of theta. It's the value at the point where Q is located, so the Q is focusing. So S naught is not constant. And this is, so simple computation shows that this is 1 over lambda square, but then I need the power here to be 1 over lambda square. So I have lambda 1/2 times then Q4, and then everything is equal to like xt over theta. Okay, so what I get is a different relation, which is lambda t plus lambda minus 3 over 2 over x of t to theta. And this is constant. In fact, if I look for any negative 0 energy, let's say, I will find that this is 0. So it's a different relation. And we happen to have a specific solution. Remember that x prime is 1 over lambda square. So it's easy to take one lambda to make the derivative of lambda. Right? So we can very easily solve this equation. And we find solutions which are different from the one we had before. We find solution like this, for example. Okay, these are solutions. And I have the expression also for the x of t. And if you take theta to be 3 over 2, we find again t minus t. But if we take theta to be less than 3 over 2, we find a graph which is quicker than 1 over t. And if we take theta bigger than 3 over 2, we find a graph which is less than 1 over t. Right? So in some sense, it's not anymore a nonlinear graph. It's a graph which is driven by a source. The source being the tail on which the solution is traveling while it's concentrating. Right? So the solution travels like this, and its dynamics is driven as the first order by the tail on which it is located. It's not anymore a nonlinear graph in some sense. But this happens in H2, in H1. So So it's a fact we have to face when we want to understand dynamic in H1. This exists. That's why I will stop here. Thank you very much. We cannot do, if you take theta small, then we get blow up in we get blow up in infinite time. And you see, if you take 504 is a threshold here. Right, so in this proof we have this some power here and then 504. If you take 504, you get something I just remember, if you take something which is less than 504, you get blow up in infinite time. And then if you take theta too small, you're not an issue. So, and on the other side, if you take theta too big, of course, at some point it does not interrupt the blow up anymore. What we cannot do is to go with powers that are too slow. So here we still have this restriction. So we don't even approach 1/3, which is a similar blow up. We are far from it. Yes, but everything is done backward. We take a final data close to the block time. We take HM to be 0 at this final data. We make the evolution. Everything is a set of estimates we have. So at a given time, we have all nice estimates. We have to at this time, and by which continuity of the flow, then we get solution which goes out with this estimate for a local time. So it's a compactness argument again. It's very similar to what we did for the mean magma solution. So, but we could imagine to do the for all guys in A. Why not? With the same. This was not done, but why not? And it's not so interesting, but it could be done. It's global, but this is the only thing we know. We know it's global because we could put that on one side it's exponential decaying. And we have another result that for exponential decaying initial data with minimal mass, there is no blow up. So the minimal mass is decaying on one side, exponential decaying. On the other side it's similar to this. It's similar to some power. So it's very asymmetric solution. We probably say that it cannot be explicit as for the Schrödinger equation. So we don't quite know what happened for backward. So what we expect is it scatters, but nobody knows how to prove it. It is in H infinity. It's very smooth. And we can also deduce some estimates close to the block time from black law. But when we go back in time, it exists the neighborhood of the solution, and then we have to stop the analysis. So it's a completely different story. We would need like a scattering theory of the sphere, or in the ball first and on the sphere for, and this we don't have it for the field equation. So. Thank you very much for the introduction. And I owe a special thanks to Lillian Diss and Demarge Schindler, who I think have been extraordinarily courageous in organizing such a big meeting and is helping to create this accident in a joint session. I think it's already a success with a big meeting. There were no disasters, but there's been nothing resembling a disaster so far, at least, so I think this is a great success.